Okay, let's dive into this. Welcome, everyone. Today, we're taking a really fascinating journey into the absolute basics of mechanical engineering design. We're going to completely demystify Section 3.1 of mechanical datasheets and take you from zero to hero. If you're a beginner just stepping into the EPC world, that's engineering, procurement, and construction, this explainer is made specifically for you. We're going to look at exactly how we define the size of these massive industrial units, relying purely on visual geometry and globally accepted terminology. So get comfortable and let's deconstruct the anatomy of these giants piece by piece. It sounds like a super simple question, right? But really think about it for a second. How do engineers actually measure this massive plant equipment? When you're handed a data sheet just packed with abstract acronyms and numbers, how do you translate that and physically visualize the giant geometry of a pressure vessel? You literally cannot just take a standard tape measure to a piece of equipment that's 3 stories tall and built to withstand extreme pressure. For everyone from the process engineer to the mechanical designer, all the way to the construction team on site to communicate these dimensions perfectly, we need a very specific, globally understood language. Now, what's really interesting about this slide is how we can visually anchor these concepts before we even think about throwing math at you. Notice how a pressure vessel isn't just one uniform shape. That straight cylindrical part right in the middle, we call that the shell. And then look at the two ends capped with those curved sections. We call those the dish head, or sometimes simply the head. Basically, every pressure vessel you're going to encounter is fundamentally made of these two geometric parts, the straight shell and the curved head. Lock that visual firmly in your mind. When we talk about cylinder-type equipment, the entire global engineering community uses a very specific, universal vernacular. We never rely on local slang or informal descriptions. The size of the equipment is primarily expressed through a combination of two key acronyms, ID by TL to TL. That's the whole shebang. Whether you're designing a plant in Houston, Seoul, or Frankfurt, if you say ID by TL to TL, every mechanical engineer knows exactly what dimensions you're talking about. It is the absolute global standard for sizing. So let's break down exactly what the first part of this equation means. Our first term is ID, which clearly stands for inside diameter. It's really crucial that we strictly stick to this globally accepted English terminology over any local translations. The inside diameter, just as the name implies, is the straight measurement directly across the inner circular surface of the equipment. We are not measuring the outside yet. We are focusing entirely, 100%, on that empty space inside. So, why do we focus on the inside first? Well, these massive vessels are formed from bent, extremely thick steel plates. The ID measures the inner surface of those plates, and that is absolutely critical because that interior space dictates the total volume of the equipment. And who cares the most about volume? The process team. They're the ones calculating exactly how much fluid or gas needs to be contained, heated, or separated for the plant to actually work. Therefore, the process team dictates the ID to ensure the vessel physically holds the required capacity. Once the process team hands us that inside diameter, how does the mechanical engineer figure out the overall external size? So the crucial point is following a simple 3-step formula. Step 1, start with the inside diameter. Step 2, add the shell thickness. But remember, because the shell wraps all the way around the equipment, you have to add 2 times the shell thickness. Step 3, that little bit of math gets you to the outer diameter, or OD. It's basic geometry, but it is the absolute bedrock of equipment design. Let's briefly contrast these two core English engineering terms so beginners can really lock in the physical difference here. ID is all about the internal volume focus. That fluid-holding interior space is the star of the show. OD, on the other hand, focuses on the external footprint, which includes that thick exterior steel wall. If you're the engineer designing the foundation to hold this giant or figuring out how to transport it on a highway, you care a lot about the OD. But if you're designing the chemical reactions happening inside, ID is your most important metric. All right, let's move to the second half of our sizing equation. We've conquered the width with ID, so now we need the length. This is where TL to TL comes into play, defining the tangent to tangent length. Now, if you aren't an engineer, that might sound a bit like jargon, but it's a highly precise measurement. TL simply stands for tangent line. But where exactly is this line? Let's move to and see how this builds on an actual mechanical drawing. You see that precise line noted as TL? That is our tangent line marker. Whenever you're reviewing vendor prints or mechanical schematics, your eyes should immediately hunt for this specific marker. It's not just a random dot on a curve. It's a very specific geometric location that defines the functional length of the vessel's body.
To break it down really simply, the tangent line is the exact boundary where the straight shell ends and the curved head begins. Remember those two shapes we talked about earlier? The TL is the same right between them. So when we say TL to TL, we are strictly measuring the length of just the straight shell section. And just a quick note, when we're dealing with vertical vessels instead of horizontal ones, the terminology shifts slightly to bottom head and top head, but the core concept of that TL boundary stays exactly the same.
And this brilliantly illustrates the ultimate aha synthesis moment. Looking right at the center, we see the inside diameter clearly mapped out, defining our internal width. And running across it is the tangent length, bounded perfectly by the straight section before any curves begin. Unifying these two metrics, the ID and the TL, on one structural diagram allows us to perfectly and precisely define the core physical size of the equipment to absolutely anyone, anywhere in the world. Now, to wrap things up, I want to leave you with a provocative thought experiment to test your new knowledge. Imagine this. What if the process team suddenly demands a massive increase in internal volume? How does that single change ripple through the ID, the OD, and the TL? Do we need to increase the ID? And if we do, what happens to the shell thickness to handle the pressure? And what does that do to our OD? Or do we just keep the ID exactly the same and stretch out the TL? This interconnected web of variables is exactly what engineering is all about. Hopefully, this explainer has sparked your curiosity and leaves you wanting to explore the full, fascinating world of pressure vessel design. Thanks so much for joining us, and keep on learning.